Okay, going to talk about problem 18.19, page 73, volume 3. We have an aluminum bar connecting two reservoirs. Let me give you a quick visual of that over here. So you can imagine, let's say we have a reservoir of boiling water. Maybe this is hot water coming from a nuclear reactor or something. And we're pumping it through here, so it's continuously being cycled in such that this reservoir right here is constantly filled with boiling hot water. I've got this aluminum bar. We see it's got some cross section. It's essentially a long straight bar with a rectangular cross section that's been bent into the shape of a U. And we're setting this system up such that we pour some ethyl alcohol in here. And the idea is we want to use this reservoir of boiling water to heat up the ethyl alcohol. Heat is going to conduct through here. There will be some losses, but we've mineralized almost everything. If we could encapsulate this thing and maybe put some more insulation around the metal so we're not losing energy to the air, that would be even better. But that gives you a visual for this problem. Let's go back to the main board. Let it focus for a second there. All right, and so here's what's going on. We have some sort of continuous heat source keeping this water boiling. Over here we have ethyl alcohol. We're going to start at room temperature, assume that's 20, and we're going to try to heat it up to 55.5 degrees Celsius in 38.5 minutes. All right, how much heat will be required? What is the length of the aluminum bar required for this final temperature in that much time? And then environmental factors. We've kind of talked about that a little bit, just the insulation and how that's going to affect things, but we'll revisit that at the end. All right, and so let's go ahead. If you want to pause the video and try to do part A by yourself, great. I'm going to proceed in 3, 2, 1. Okay. Q equals MC delta T. This marker doesn't make me happy. Let's try this one. It's a little better. Is there one other one? Let's try this other one. What's the mass I want to use? I'm going to go 0.222 kilograms instead of grams. Why? Because if you look up on the tables in this chapter, there's a bunch of tables, pages 69 has some tables. Where's the other tables? Probably 72 or something like that, 73. Yeah, page 72 also has some tables. So there's a bunch of tables with constants. And C for ethyl alcohol is 2,400 joules per kilogram per Kelvin. All right, and so now you can see why I chose that. And then delta T. So we're heating this up from 20 to there. That delta T is 35.5 degrees Celsius, which if you punch in the numbers, you get 17.338 kilojoules. Now, a note on rounding. Typically, we want our final answers to be correct to 3 digits. I know we're going to use this result in the next one, so I'd want to round to 4 digits. But because the first digit is a 1, a lot of times we keep an extra digit for those. But just to keep track of the sig figs, it's probably only 2. So this is right, I don't want to introduce rounding error. That's enough on that. Part B. What is the length of the aluminum bar? If you want to try this yourself, pause the video. I'm going to proceed. 3, 2, 1. All right. The heat, what transfer mechanism is being used? This is not radiating from here to there. It's not a convection current from here to there. It's conduction. Just like electricity could conduct through this bar, thermal energy can be transferred like a current through that bar. This is a thermal conduction problem. I'm going to write that down. I know that power equals Q over delta T. I'll say approximately equals that. Equals Ka delta T over L, where L is the length of the rod. Now, this equation is valid in steady state. What does steady state mean? Things aren't changing. Is that really true for this problem? Maybe, in fact, why don't you, the main thing, this is a constant, area is something that we know, length is something we're trying to figure out, Q is something we kind of know, time is something we know. The only variable here that's interesting is delta T, that's a capital T. If you think you know what that is, why don't you pause the video and think about delta T and think what you would put for delta T. Pause the video and actually try it. I'm going to proceed in 3, 2, 1. This is tricky. Okay, initially, so first off, delta T is not 35.5. That's the increase in temperature of the ethyl alcohol. For this equation, delta T means the temperature difference between the two reservoirs. We know this water is boiling, so this is at 100 degrees Celsius. Initially, delta T is 80. But as this thing heats up, delta T is going to keep getting smaller and smaller, right? So when it gets up to about 50 degrees, delta T is only 50. So what delta T might we use? And why is it still okay to use it? Well, things are not going to change that rapidly. So for at any given second, the temperature difference is approximately constant. It is creeping up, but it's changing slowly over 38.5 minutes. So what we could do here is maybe just get the average temperature. So let's see what we get. T average between this and this, you add those together, divide by 2, what do we get? 37.75, is that right? Let me think. Got it written over here. Yes. So now delta T on average would be the hot reservoir temperature minus the average temperature of the ethyl alcohol, which is 62. You may be saying, why are you keeping these to 4 sig figs? I don't want to introduce intermediate rounding error. I keep an extra sig fig till the end of the problem, and then we can always deal with the rounding at the end. So the delta T that you use for the Q equals MC delta T is 35.5. The delta T we're going to use down here is this 62.25. All right. Now, out of all this, we could rearrange this and solve for L. L is going to equal moving this up, moving this up, moving this over. Rearrange that. Pause the video. See what you get. I'm going to get, or just erase me. L is K A delta T, delta little t, all over Q. So in this case, maybe we should check the units. The units of K are watts per meter Kelvin. Area is going to be meters squared. Aha, I can see I better convert that. Okay. Delta T is Kelvin. You can say degrees Celsius, that's fine. And then delta T is seconds. And then all of this is divided by Q. That's 1 over joules. So now we could see what this works out to. We want to get a length of meters. A cool trick here is to remember a watt is also a joule per second. And now let's check this out. Seconds drop, Kelvin drops, joule drops. We get a meter. So this is looking good. All right. When I plug this all in, now that I've checked the units, I could just write the numbers down. K is, I looked up on one of those tables, what was it? It was 220, probably 2 sig figs. Remember when you're looking up numbers in the tables, everybody's table might be a little bit different. These numbers are great for an approximation, and we're getting a good estimate for prototyping. They don't have to be exactly the same as every table's a little different, whatever. Converting that, you should find 275 times 10 to the minus 4th meters squared. centimeters squared. You have to divide by 100, but then square it, so you're dividing by 100 squared, that's 10 to the fourth. That's the same as multiplying by 10 to the negative fourth. Delta T was this one. I guess yeah, okay, whatever. I've already done the units. The time, better get that in seconds. That turns out to be 2310 seconds. And then all over, we want to use units of joules, so 17.338 times 10 to the 3 joules. And out of all that, I think I found, what did I get? If we keep track of the sig figs, right, we're assuming this one was only the second. So we're assuming this is about 50 centimeters. So in this case, this actually gets very close to the exact answer, and I'll show the exact answer to 18.19 in the next video, just so this one doesn't get too long. But this gives you an idea of how to do that. Environmental factors. All right, so in reality, we know we're losing heat out the top of that metal rod. So if you recall, let's go back to this picture, right? We're losing heat. So in order to get this to transfer more rapidly, think, do we need a shorter rod or a longer rod? Shorter. So, right, with ideal conditions, we expect this would have to be 50 centimeters long. But if we're losing tons of heat out the top, maybe it needs to be a little bit shorter. Okay, so that, and obviously this is not to scale, but going back up to the front, see if there's anything else we need to discuss. So the big factor is we're constantly losing energy to the surroundings. You could even argue, yeah, you're losing some through the sidewalls of the styrofoam, but that's probably negligible to how much is radiating away and convecting away from the aluminum rod. But all those factors contribute, so you'd expect in practice, you'd have to use less distance than 50 centimeters due to all those heat losses to the environment. All right, I'll do the exact solution in a minute.